So we went and showed that the t-test is basically a special case of a one-way ANOVA, which sort of makes sense because, you know, one-way ANOVAs are 3 groups, 4 groups, 5 groups, 6 groups, so why wouldn't they work on 2 groups? Well, they do. But why is there this connection between linear regression, where you have a continuous variable versus another continuous variable, and ANOVAs, where you have these factors, right? And this is really important, right? This idea is behind all modern statistics, and really helps you get to grips with a lot of more complicated statistical stuff that you're probably not going to have to deal with for a long time, but is still super important. Okay, so we know, right, that when we did our linear regression, we fit the straight line. Here's the general equation for a straight line: y equals mx plus c, where m is the slope and c is how far up and down the y-axis it goes, right? And so it should seem no great surprise that you're fitting this equation to your data when you fit a line. But what if I told you were fitting basically the exact same equation whenever we did an ANOVA or a t-test? All right, so here's this t-test data we had before. We can actually change that data. It's still the exact same data. We can change how it's represented by showing it like this. Right, so here's all of the reaction time. So it's just a one big column of the dependent variable. And then we have this another variable called right hand, which is 0 when it's the left hand data and 1 when it's the right hand data. This conversion is called converting it to the long form of the data. In this case, it's not particularly, well, it's still longer, but in a lot of data, the data would go from being very wide, this is the wide version, to the long version. All right, but that aside, what the important thing here is, by doing this, we can now fit a line, that was inverted commas, air quotes, sorry, we can fit a line to this data. And how do you do it? Well, here's our general equation for a line, y equals mx plus c. Y becomes our reaction time. Beta 1, we're just going to call it beta 1, is for our slope, and our offset is beta 0. And so what would just happen, right, if we just put this data into Excel and fit a line to it? Well, you would get these results. Beta 0 would be 257.8 and beta 1 would be minus 20.67. That's what would happen if, you just put this data into Excel, you never told it, you had plans on statistics, or you just fit a line to that data. This is what you would get. Interestingly, the mean for the left hand is 257.8. What is fit to the offset? And the beta 1, which is minus 20.67, well, that is what you would get if you took the mean of the left hand and if you took the mean of the left hand, you subtracted off this 20.67, you would get the mean for the right hand. So it's fit a line that goes between the right hand value and the left hand value. You could do the same thing, right? For the ANOVA case, here is our ANOVA data, right? Here it is in the wide form, here it is in the long form, where we have 1 for the Mozart data. Here you can see it's the 58, it's the 56, it's the 57, there they are, 58, 56, 57. Here's listening to relaxation. There's the one there, 53, 54, 53, 53, 54, 53. We don't need to put in another column with ones for the silence, because it will know that when both of these are 0, that must be the silence case. And again, if we tried to fit this, we would now need 3 coefficients, 1 for the silence, 1 for the relaxation, and 1 for the Mozart. Now, what am I doing here? Why am I saying times Mozart times relaxation? Well, when Mozart, let's look at this one, right? It's trying to fit this value here. So Mozart is 1, so this takes on 1. Beta 1 is the coefficient for relaxation, and relaxation is 0 for this. So this times 0, that turns to 0, and plus beta 0. So what do we end up getting? Well, we end up getting that beta 0 is the silence mean. So when that term and that term is 0, we're left just with beta 0, which is the mean of this data down here. Then beta 1 is 2.92, which is the difference between the silence group and the Mozart group, and 0 minus 0.26 is the difference between the silence group and the relaxation group. All right, so why are we doing this, right? We are doing this because now we can treat both the linear regression and the ANOVAs all in the same way. They are all equations where we say y equals beta n times xn. So beta is the coefficient we fit, xn is the input to the model. It can either be a 1 or a 0 in the case of an ANOVA, or it can be a continuous variable in the case of a linear regression. And we just add them up with all of these terms. And we fit the values, and then we can do the ANOVAs on the best fit of that model, right? Because we need to be able to calculate the best fit, because it's the difference from the best fit gives us our residual sums of squares. Now, this idea that linear regression, t-tests, and ANOVAs are all about fitting equations and coefficients is called the general linear model, and it was quite a revelation when it was sort of discovered in the 70s.